need to verify a claim by gathering evidence across multiple sources, without manually sifting through search results. You'll see how to chain together query generation, document retrieval, and evidence extraction in a loop that automatically refines its search, compiles notes, and tracks sources, all in a single reusable module.
Class hop DSPy module. Def init, self, numdocs equals 10, numhops equals 4. Self numdocs, self numhops equals numdocs, numhops. Self generate query equals DSPy, ChainOfThought claim, notes query. Self append notes equals DSPy, ChainOfThought claim notes context new notes. List SDR titles, list SDR. Def forward, self claim, SDR list SDR. Notes equals, titles equals. For in range self, numhops. Query equals self, generate query, claim equals claim, notes equals notes. Query. Context equals search, query, K equals self, numdocs. Prediction equals self, append notes, claim equals claim, notes equals notes, context equals context. Notes, extend prediction, new notes. Titles, extend prediction, titles. Return DSPy, prediction notes equals notes, titles equals list, set titles.
This demonstrates a multi-hop retrieval-augmented generation architecture, where each iteration dynamically refines both the search query and accumulated evidence. The pattern chains together reasoning and retrieval steps, progressively building a knowledge base through successive cycles of query generation, document retrieval, and evidence extraction. Unlike single-step retrieval, this approach creates a feedback loop where each iteration informs the next, enabling deeper evidence gathering. The implementation separates concerns into two specialized chain-of-thought modules, one for query generation and another for evidence processing. During each hop, the system formulates an optimized search query based on current findings, retrieves relevant documents, then extracts and consolidates new information while maintaining source attribution through title tracking. This modular design allows the system to preserve context across iterations while keeping the reasoning process explicit and auditable. This approach solves the problem of incomplete evidence retrieval for complex claims where single queries often miss critical information. The iterative method excels in scenarios requiring comprehensive evidence synthesis, such as fact verification or multi-document question answering. While introducing additional computational overhead through multiple LM calls, the trade-off delivers more thorough and attributable results than traditional single-step retrieval methods. Let's break it down line by line.
Class hop DSPy module.
Defines a custom DSPy module named hop that extends DSPy module. This establishes the foundational class structure for implementing multi-step reasoning, where the forward method will later define the iterative retrieval and generation process.
Def init, self, numdocs equals 10, numhops equals 4.
This constructor initializes the hop module with two key parameters. Numdocs controls how many documents are retrieved per search iteration, while numhops determines the number of iterative reasoning steps. The defaults, 10 documents, 4 hops, provide a practical starting point for multi-step retrieval-augmented reasoning.
Self numdocs, self numhops equals numdocs, numhops.
Initializes and stores the two core configuration parameters as instance variables. Numdocs controls how many documents to retrieve in each search iteration, while numhops determines the total number of reasoning iterations the system will perform. This single line efficiently sets up the operational constraints for the entire multi-hop retrieval process.
Self-generate query equals DSPy, ChainOfThought claim, notes query.
This initializes a chain-of-thought module that generates search queries by reasoning over the current claim and any accumulated notes. The input-output signature explicitly declares it, takes a claim and notes, then produces a refined query string for the next retrieval step.
Self-append notes equals DSPy. Chain of thought, claim, notes, context, new notes. List SDR, titles, list SDR.
This initializes a chain-of-thought module that processes the current claim, existing notes, and retrieved context to generate two outputs, updated evidence notes and their source titles. The signature defines the exact input-output contract for each reasoning step in the multi-hop process, with the list SDR annotations ensuring structured, type-consistent results.
Def forward, self-claim, SDR, list SDR.
Implements the core reasoning workflow that processes an input claim through iterative evidence gathering. The method signature shows it takes a string claim and returns structured results, forming the backbone of this multi-hop retrieval system. Each call to forward executes the complete reasoning pipeline defined in the class.
Notes equals.
Initializes an empty list to accumulate retrieved evidence across multiple search iterations. This serves as the working memory that will collect relevant notes during the multi-hop reasoning process.
Titles equals.
Initializes an empty list to track document titles collected during the multi-hop retrieval process. This enables the system to maintain and return a record of all evidence sources used to build the final response.
For in-range self, num hops.
This loop drives the multi-hop reasoning process, executing once per hop to progressively refine evidence. Each iteration generates a new search query from the current notes, retrieves documents, and accumulates findings. The underscore variable indicates we only care about completing the specified number of iterations.
Query equals self. Generate query, claim equals claim, notes equals notes. Query.
This invokes the generate query chain-of-thought module, passing the current claim and accumulated notes to produce a focused search query. The module uses the existing context to refine what to search for next, implementing the iterative retrieval pattern. The query property extracts just the generated search string for the retrieval step.
Context equals search, query, k equals self, num docs.
This calls an external search function with the generated query, fetching the top numdocs most relevant documents. These retrieved documents form the evidence base that the next step will reason over.
Prediction equals self. Append notes. Claim equals claim, notes equals notes, context equals context.
This invokes the append notes chain-of-thought module to process the current claim, accumulated notes, and retrieved documents. It returns a structured prediction containing updated evidence snippets and their source titles, which are then merged into the running lists for the next iteration. The pattern enables progressive refinement of evidence across multiple hops.
Notes, extend prediction, new notes.
This accumulates new evidence from each retrieval hop into the growing notes list. The extend operation preserves all intermediate findings, enabling the system to build a comprehensive response across multiple search iterations.
Titles, extend prediction, titles.
Extends the titles list with new document titles retrieved during each hop. This preserves all contextual references across iterations, maintaining a complete record before deduplication in the final return statement.
Return DSPy. Prediction notes equals notes, titles equals list, set titles.
This returns a structured DSPy. Prediction containing the accumulated notes and a deduplicated title list. By converting titles to a set, then back to a list, it eliminates duplicate entries that may have been collected during the multi-hop retrieval process. Multi-hop reasoning architecture. This hop module demonstrates DSPy's iterative retrieval augmentation pattern, where each forward pass generates a query from accumulated notes, retrieves new context, and appends refined observations, all while maintaining the original claim as the anchor. The numHops parameter directly controls reasoning depth, but increasing it without adjusting numDocs risks overwhelming the LM with repetitive or tangential context. ChainOfThought modules here serve dual purposes. Query generation focuses outward on information needs, while note appending synthesizes inward. Both must handle growing note lists without losing thread coherence.
The hop that returns to its beginning was never moving.